Okay. I'm gonna get started. So, the chapter 6 homework is due today, the 19th. The chapter 7 homework will be due on the 8th. The chapter 7 quiz will also be on the 8th, and that will be in lecture. No, wait, no. That will be in SI, my other class it's in lecture. Sorry. Thing. Let me just check what I have on the schedule. Did work this out. Wrong class. Courses. No worries, it's all out. It's just easy for me to get two classes confused. Yeah, so it'll be in the SI session. Sorry, the chapter 7 session quiz will be in the SI session on Monday. On the 8th. And the other class where it's going to be in lecture. Again, all remaining lab dates are for makeups. So everybody who's here, I think, has all their labs done. And then on the 8th, we'll have a review of chapters 5, 6, and 7. And on the 10th, we'll have exam number 3 on chapters 5, 6, and 7. So we were discussing spherical mirrors. Spherical mirrors are a section of a sphere with a radius r and a center of curvature c, like so. That's actually, I believe these are actually parabolic. They get the exact effect. Exact illusionary effect they're going for, but and the geometry of a spherical mirror can be described using several terms. It has a radius, a center of curvature for the entire sphere. There's a radius and a center of curvature for the entire sphere. There's a principal axis, which is a line drawn through the center of curvature to the mirror's surface, and the vertex is the point where that principal axis intersects the mirror's surface. And then there's a focal point and a focal length. So spherical mirror sex sort of like an approximation of the ideal parabolic mirror. But what will happen is that lines coming in parallel will be focused to the focal point, which is halfway between the vertex and the center of curvature. So the focal length is half the radius. Half equal radius over here. And there's two types of spherical mirrors. There's a concave mirror, like I was showing there. That's the inside surface of a spherical section. It's concave because it's like a recess or a cave. This is also a converging mirror because parallel light coming in gets brought together to a point. Incoming light rays that are parallel to the principal axis will converge and pass through the focal point. Incoming light rays that are not parallel to the principal axis will converge on the focal plane. So here, incoming parallel light rays converge at the focal point. And images will form along the focal plane from incoming rays not parallel to the principal plane. You can also have a convex or diverging mirror. This is the outside of the spherical section. Incoming rays that are parallel to the principal axis are reflected so that they appear to diverge from the focal point. And then non-parallel rays coming to the mirror are made parallel to the principal axis. So they would be going to the focal point, they end up parallel. This causes the viewer to have an expanded field of view. So if you have principal ray, the parallel rays coming in, they act like they were coming from the focal point. And images formed by spherical mirrors can be solved graphically using ray diagrams. We commonly use an arrow to represent the object because it has a clear direction, it has a top. And the location, orientation, and size of the image can be determined by drawing two rays. The first ray is drawn parallel to the principal axis and then gets reflected through the focal point. The second ray is drawn through the center of curvature to the mirror surface and then is reflected directly back. And the intersection of these two rays is the position of the image. As you can see here, we have an object, we draw a line parallel, it goes through the focal point. We also draw a line through the center of curvature, which bounces back, and the intersection of those two lines, two rays, is here, and that's where the image forms. So here is what you get if you have an object located beyond the center of curvature. You get an image that is real, inverted, and smaller than the original object. Here we have an example of an object located between the focal point and the center of curvature. You get an image that is real, inverted, and larger than the object. So here you go, parallel to the mirror through the focal point and through the center of curvature, bouncing back and out. And lastly, if you have an object inside the focal point, here's parallel to the mirror through the focal point, and here's bouncing through the center of curvature. Here the image is on the far side of the mirror. It's virtual, it's upright, it's larger than the object. You'll have to extend these lines out. And the characteristics of images can be described in the following manner. An image can be real or virtual. A real image is one you can project on a screen. So the image here on the screen is a real image. An image can be upright or inverted. Is it right side up or upside down? An image can be larger or smaller than the object. There's a general pattern. Real images in simple situations with just one mirror or just one lens. Real images are inverted, virtual images are upright. Now, the image characteristics are determined by several criteria, including the object's distance, so the distance of the object from the vertex, the focal point of the spherical mirror, and the size and orientation of the object. And the distance of the image from the vertex is called the image distance. And if you know the focal length and the object distance, you can find the image distance with this formula. 1 over focal length is 1 over distance to the object plus 1 over distance to the image. So if you're trying to find the image distance, that works out that the image distance ends up being 1 over focal length minus 1 over object distance. And if the image distance is positive, the image is real. If the image distance is negative, the image is virtual. So a real image is an image for which the light rays converge so that an image can be formed on a screen. Real images form in front of the mirror where a screen can be positioned. Like you're seeing here, there's actually a mirror in this projector forming this image. And virtual images are an image with the light rays diverge and cannot form on a screen. Virtual images form behind or inside the mirror where the light rays appear to converge. This is what you see when you look at yourself in the mirror. And a virtual image results when the object is inside the focal point. So here's a concave mirror showing a real image. Just a sec. Reload. There we go. Why are you not working? You were working earlier. Let me just check something real quick. This is the only one. Let me unhide this. This is why I keep these around, even though they're going to have an ad, which is what I was trying to avoid. Not want to happen. Buggy.
Mirage, an extraordinary optical toy, one of the best ever made. This little piggy went to market. Well, I think it's a pig. It looks pink, and I should be able to pick it up, but it's just not there. I'll try poking it. No, nothing there either. Of course, it's a mirage, for when I lift up the top parabolic mirror, there the pig is really inside, quite real and quite solid. But when I replace the top parabolic mirror, there he is in a mirage form, looking as though he's standing on a little curved mirror. The mirage.
So you can also construct ray diagrams for convex or diverging mirrors. Same two rays are drawn, but they have to extend through the mirror. The image in a convex mirror will always be virtual, upright, and smaller than the object. So here the image is virtual, upright, smaller than the object. So here, if you have an object placed 25 centimeters in front of a concave mirror and construct the diagram, you're given C is 20 centimeters and therefore F is 10 centimeters. Then you can work out, so 1 over 10 centimeters equals 1 over 25 centimeters plus 1 over distance to the image. 1 over 10 centimeters minus 1 over 25 centimeters is, so this is 2 over 50, this is 5 over 50, so 3 over 50 centimeters. So DI equals 50 over 3 centimeters, which is 16.67, 16 repeated. So about 16.7. Let's see if I got that right. No. Here we have an object 15 centimeters in front of the convex mirror. We want to construct the ray diagram. Again, we're given that C is 20 centimeters and the F is therefore 10 centimeters. So you can draw this and get the image forms further away here. So here this is 1 over 10 centimeters is 1 over 15 centimeters plus 1 over DI. 10 centimeters, 1 over 15 centimeters. This is 3 over 30, 2 over 30, gives you 1/30 centimeters equals 1/di. So di equals 30 centimeters. So, here's a problem. An object is placed at a distance of 25 centimeters from a concave mirror of focal length 10 centimeters. Is the image formed real or virtual? Is it upright or inverted? And is it larger or smaller than the object? So I'll let you think about that for a bit. So that's 25 centimeters away from a concave mirror of focal length 10 centimeters. That will put it beyond the center of curvature, which is at twice the focal length. The center of curvature is at twice the focal length, so at a distance of 20 centimeters. So this is beyond that center of curvature. So this is forming an image when the object is beyond the center of curvature. It looks something like this. The distances aren't exactly right. So the image will be real, inverted, and smaller than the object. Here we have an object at 15 centimeters from a concave mirror with a focal length of 10 centimeters. Is the image larger or smaller than the object? Is it real or virtual? Is it upright or inverted? And is it larger or smaller than the object? And if you do want to work out the exact size of the image compared to the object, you don't need that for this class, but the magnification, the change in size, the magnification, the size of the object compared to the original is distance to the is minus. It is minus distance to the image over distance object. The minus sign is because real images, which have a positive DI, are inverted. So this we worked out. DI here is 30 centimeters. Here the image is real, upright, inverted. Real images are inverted. This is between the focal point and the center of curvature. Real, inverted, and larger than the object. And now we have a thing that's closer to the mirror than the focal point, between the mirror and the focal point. Is the image formed real or virtual? Is it upright or inverted? Or is it larger or smaller than the object? So here, the closer you get to a mirror, the more it acts like a plane mirror, a flat mirror. Here, the image will be virtual, larger than the object, and upright. Virtual and upright, and larger than the object. And then lastly, we have an object 15 centimeters from a convex mirror with a focal length of 10 centimeters. So is the image formed real or virtual, upright or inverted, and larger or smaller than the object? So all images with convex mirrors will always give you an image that is virtual, upright, and smaller than the object. Doesn't matter where you are. You always get something virtual, upright, and smaller than the object. So to find the location of an image for a mirror, 1 over the focal length, which is positive for concave and negative for convex, equals 1 over the object distance plus 1 over the image distance. So DO is the distance from the mirror to the object, DI is the distance from the mirror to the image. DO will be positive, DI is positive if the image is real, and negative if the image is virtual. So if an object is placed at a distance of 3 centimeters from a concave mirror or focal length 2 centimeters, where does the image end up? So 1 over focal length equals 1 over DO plus 1 over DI. We can now plug in the things we know. The focal length is 2. The object distance is 3 centimeters. So 1/2 equals 1/3 plus 1 over DI. So we subtract 1/3 from 1/2, we get 1/6. So that's 1 over DI. DI equals plus 6 centimeters. That means the image is real. Therefore, it will be inverted. And it's further away from the mirror than the object, so it will be bigger than the object. In fact, it'll be twice as big. So the image is real and 6 centimeters in front of the mirror. And it'll be inverted and bigger than the object. Now, the other way we can focus light is with a lens. Mirrors focus light with reflection. Lenses focus light with refraction. They bend light by passing it through a different material. They consist of some material, plastic or glass, that refracts light waves to give an image of an object. There are 2 main classes of lenses. There are converging lenses, which are convex. So convex lenses are converging, opposite to the way mirrors. Converging mirrors are concave. Converging lenses are convex. They're thicker at the center than the edge. Diverging lenses are concave. They're thicker at the edges than the center. So these are converging or convex lenses. Their greatest thickness is at the center. These are diverging or concave lenses. Their greatest thickness is at the edge. And rays principal to the parallel axis will pass through the lens and converge at the focal point on the opposite side of the lens. And rays going through a diverging lens will appear as if they came from the focal point on the same side as the lens that they're coming from. So for a diverging lens, rays parallel to the principal axis appear to diverge from a focal point on the incident side of the lens. I probably should have repeated that. So ray diagrams for lenses are much like ray diagrams for mirrors, but now you're going through the lens. So with the lens, you draw one line ray parallel that goes through the focal point on the opposite side, and then another line that goes through the center of the lens and comes out the other side. That's one way you can do it. You can also do a line that goes through the focal point on the near side and comes out parallel. So images formed by refraction of light through a lens can be constructed by a graphic procedure similar to those for spherical mirrors. And the location, orientation, and size of the image can be determined by drawing two rays. In order to construct ray diagrams for lenses, only the focal points for the respective surfaces need to be known. So the first ray is drawn parallel to the principal axis and then gets refracted by the lens through the focal point of the lens. And then the second ray is drawn through the center of the lens with no change in direction. And the tip of the arrow occurs where these two rays intersect. The other way is you could draw a line from the top of the arrow through the focal point and then come out parallel, and that would also be. If the object is beyond the focal point, an inverted real image is formed, and the image becomes larger as the focal point is approached. If it is within the focal length, the object forms a virtual image on the object side of the lens that is bigger than the object. This is what you're doing with a magnifying glass. You're bringing the object within the focal length of the magnifying glass, and so you see a virtual image of it that is larger. And it will be on the same side of the lens as the object. And for a diverging lens, the image is always upright and smaller than the object. And so if a convex lens has a focal length of 12 centimeters, we can draw ray diagrams for an object 18 centimeters from the lens. And we will get an object that is larger, an image that is real, inverted, and larger than the object. Here is one with the same lens, 12 centimeter lens, but now the object is 8 centimeters from the lens. So now we're inside the focal length. So we get a virtual image that is bigger than the object. This is acting as a magnifying glass. So here we have an object placed at a distance of 25 centimeters from a converging lens of focal length 10 centimeters. Is the image formed real or virtual? Is the image upright or inverted? And there's the image on the same side or the far side of the lens. So we have an object that is beyond the focal length point of a converging lens. We're going to get a real image. It will be inverted, and it will be on the far side of the lens. The image is real, inverted, and on the far side of the lens. Here we have an object at a distance of 5 centimeters from a converging lens of focal length 10 centimeters. And I forgot to put an animation on that image. Oh well. Is the image formed real or virtual? Is the image upright or inverted? And is the image on the same side or the far side of the lens? So here, as you can see, the image is virtual on the same side of the lens as the object and upright. Virtual, upright, same side of the lens. And here we have an object placed at a distance of 25 centimeters from a diverging lens of focal length 10 centimeters. So is the image formed real or virtual? Is the image upright or inverted? And is the image on the same side or the far side of the lens? So here we have a diverging lens, and for a diverging lens, the image is always virtual, upright, and on the same side of the lens. And the formula for the lens formula, looks surprisingly similar to the mirror formula. It's exactly the same, but you just need to pay attention to where things are located for positive and negative. It's the only real difference. So F is the focal length. Focal length is positive for converging lenses, negative for diverging. Remember that a converging lens is convex, while a converging mirror is concave. Again, positive for converging, negative for diverging. DO is the distance from the lens to the object. DI is the distance from the lens to the image. However, this is opposite to mirrors. If DI is positive, it is on the far side of the lens. With mirrors, if DI is positive, it's on the same side of the mirror because it's reflecting back at you. So negative distances are virtual images on the near side of the lens. Positive distances are real images on the far side of the lens. So here we have an object placed at a distance of 15 centimeters from a converging lens of focal length 10 centimeters. Where is the image located? All the work written out in the previous problem. So 1 over focal length equals 1 over DO plus 1 over DI. So 1/10 equals 1/15 plus 1 over DI. 1/10 minus 1/15 is 1/30. So DI equals plus 30 centimeters. The image is real and 30 centimeters from the lens on the side opposite the object. And it will be inverted as well. Yes, if there's only one lens or mirror involved. So for this class, yes. You can have real images that aren't inverted, but you need multiple optics to pull it off. Now, the human eye has a lens in it. It's a converging convex lens. And the convex lens focuses by entering light onto an area on the back of the eye called a retina. So we can focus at different objects of different distances. So we focus the light on one place called a retina, which doesn't move. And we have photoreceptors that are called rods and cones located on the retina. And the rods are more sensitive and are responsible for light and dark vision, while cones are responsible for color vision. And the rods and cones on the retina are connected to the optic nerve, which is in turn connected to your brain. sending signals in. And because it evolved and was not designed, there's like a blind spot in the middle because they wired it backwards, effectively. Like if you look at the design of the human eye and analyze, it's like this was designed by an idiot. I mean, it works, but it's got a bunch of weird mistakes in it that you would fix where you were actually intelligently designed. Octopuses and squid have better designed eyes. But there's a particular thing where we have something where, for some silly reason, something has to pass through the retina, so there's a hole there, so nothing is being detected. And that's, of course, in the middle of our field of view. So we have a blind spot in the middle of our field of view. But it has to do with how the optic nerve is connected, because it's connected to the front instead of the back. So even though the image is focused on the retina upside down, our brain just flips it. And I believe that, like, if you wear glasses that flip the image on you consistently, after a while, your brain will just flip it. They're plastic enough to do that. And since the distance to the objects varies, but the distance to the image can't change, so DO is changing, DI is fixed because you can't change the shape of your eye, the size of your eyeball. So what we do is we change our focal length. We change the shape of the lens. So the focal length of the lens must also vary. And we do that because we have muscles around our lens that squeeze or stretch the lens to change its shape. For a camera, you can't change the focal length of the lens, and DO varies. So if you've ever noticed when you focus a camera, the lens moves in and out, that's because it's varying DI to get things in focus. And as we know, not everybody's vision is perfect. And generally it gets worse as you age. So within the realm of normal, there's a number of common defects with vision. So the two most common are nearsightedness and farsightedness. Nearsightedness occurs when your lens focuses the image too far forward. So this is the ability to see nearby objects clearly, but not distant objects. What happens is your images form in front of your retina. And to fix this, you use glasses with diverging lenses that basically adjust the focal length of your eye and correct this common defect. The other issue, this also happens. Yeah. So this is nearsightedness. The other is farsightedness. This is the ability to see distant objects clearly, but not nearby objects. Here, the image forms behind the retina. And so you use glasses with converging lenses to correct this common defect. For farsighted, this is what reading glasses are for. And I think it's farsightedness that kicks in as you get older, as your lens becomes less plastic as you age. It's just like as you get older, your lens becomes less flexible. So it has some trouble and you end up more likely needing glasses. So farsightedness, it focuses on the back, and you use glasses with converging lenses to correct that defect. And the near point is the position closest to the eye where objects can be seen clearly, and your near point changes with age. Children can usually focus on objects as close as 10 centimeters. Young adults, it's something like 12 to 15, and adults past 40 start having trouble focusing on objects any closer than 25 centimeters. And as your person grows older, your lens becomes less deformable and therefore can't focus as well. Doesn't distort as much. And of course, we have ways to correct this. The ability to improve there's LASIK where you adjust the cornea of your eye to act like a lens to correct for your vision defects. You change the shape of the cornea. You can actually have artificial lenses. I think my parents have artificial lenses. At least one of them does. Where they literally cut out your old lens and replace it with a new fake one. But yeah. We were talking about lenses. And the lens formula is the human eye. So we were talking about electromagnetic radiation. I'll cover a little more. So light waves are transverse electromagnetic waves with both an electric and magnetic field vector. That means any given light source generally emits light waves that are randomly oriented. If I just have some light source, its light waves are going to be every which way. It has a mixture of waves in every direction. But certain effects can cause things to become more polarized. The directions are more lined up. Reflecting off of surfaces is actually one of these. And you can completely polarize with something like this. This is a polarizing filter. It polarizes light. I'm not sure which way. So all of them are lined up together. Let me just check. So these two polarize light in the same direction. And if I rotate, you'll see no light goes through. Because one is polarizing the light up and down, and the other one only lets horizontal light through, so it gets blocked. And if you do it partially, it's partially full. Some of it makes it through. So that's polarization. If you have polarized sunglasses, it turns out when light glare that reflects off of objects gets partially polarized like this. So if you block the vertically polarized light, is it more horizontally polarized or vertically polarized? I'm going to remember. If you block the appropriate direction of polarization, it particularly cuts out glare. So that's why polarized sunglasses are so great when you're driving and cuts off glare, which can be very blinding. And humans have no special ability to detect polarized light. Some animals can differentiate between different polarizations, like mantis shrimp. Mantis shrimp have all the vision detection. So polarization is the preferential orientation of field vectors, and the polarization of light can be attained by several means, the most common of which is to use a polarizing or Polaroid film. Polaroid cameras are made by the Polaroid company, who made money by making polarizing films originally. And this type of polarizer only allows the components of waves in a specific plane to pass. It's hard to tell if it's only allowing the vertical component or only the horizontal component here. And the human eye can detect whether light is polarized or unpolarized. So here's a short video about polarized light and how the study of the polarized light from around a black hole is actually quite interesting, because it tells us things about the magnetic fields around that black hole.
What is polarization? Light bouncing off objects allows us to see them. Light is an oscillating electromagnetic wave. We see different frequencies of that oscillation as different colors. The electric field component of a light wave can oscillate in any direction perpendicular to the direction of travel. Light from the sun oscillates in all directions. We say it is unpolarized. If the waves have a preferred direction of oscillation, they are polarized. For example, light from your phone is vertically polarized. Your polarized sunglasses are a polarized filter. Here, they let vertical polarization through. If we rotate them, almost all the polarized light gets blocked. Light produced by a torch is unpolarized. When we place a polarized filter in between, the light becomes polarized. In space, randomly moving hot gas or plasma emits unpolarized light, like the torch. Plasma threaded by a magnetic field is ordered and the emitted light is polarized. The magnetic field acts as a polarized filter. The strong gravity near a black hole bends the magnetic field and twists the polarization direction of the light from the surrounding plasma. The polarized light rays that manage to escape travel to a distant camera. The intensity of the light rays and their direction are what we observe with the Event Horizon Telescope. Using this knowledge, we can map out the magnetic fields that surround black holes.
And the reason the light from your phone is polarized vertically, well, the reason it's polarized is because the pixels on your phone are turned on and off by adjusting polarization. LCD screens work by adjusting polarization. Yeah, well, okay, so when light reflects off a surface, it ends up horizontally polarized. That's what it was. I always get that confused. So here with polarized light passing through two parallel polarizers, half the light gets through when it goes through the first polarizer, and then all the polarized light goes through the analyzer. But the light passes through the first polarizer, but will not pass through the second polarizer if they're at right angles. That is what's happening when I do this. So here, this is polarizing the light you're seeing vertically, I believe vertically. And then this is a horizontal filter. The one in front is a horizontal filter, and it's blocking the light. I think that's what you should be doing. I'm seeing it from the other side. But that's really good. Well, it's just the order. But here, yeah, as the light comes through, you can see it's completely black. But if I rotate it, light goes through. And then if halfway, partial blocked. So the way LCD screens work is that they basically have this set up, something like this set up, but the liquid crystal bends the polarization, and the amount it bends the polarization can be adjusted with electricity. So you can bend it enough to pass through or not enough to not pass through. And polarization is something that can only happen.
Now, you might be wondering, is light a transverse or a longitudinal wave? How could we test this? This device is called a polarizer. It's designed to let waves get through in only one direction. As I send the wave out, it gets through fine that way, but this way, I can't get the wave through. No matter what crazy wave I send, only the left and right components get through. It's been polarized. Now that only works on transverse waves. If it works on light, then light is a transverse wave. Because light can be polarized, we know it's a transverse wave. This is a polarizer. It's polarizing up and down. This is another polarizer. It's polarizing left and right. When these two are crossed, we get absolute darkness, zero transmittance. But if we cross them the other way, light still gets through. They're polarizing together the same way. Unpolarized light, for example, from the sun, travels to a polarizer, which polarizes it up and down. The light continues and hits another polarizer, but this polarizer is side to side. That cancels all the light. No light gets through.
The polarization of light is an experimental proof that light's a transverse wave. Longitudinal waves like sound can't be polarized. And polarizing sunglasses, when light reflects from the surface of ground or water, it gets partially polarized horizontally, and these increase the intensity and are seen as annoying and dangerous glare. But if you wear vertically polarized sunglasses, they don't allow the vertical component of light to pass and therefore significantly reduce glare. And LCD screens use polarization to make pixels. I think
LCD screens are cool. But how do they work?
Liquid crystal displays, or LCD screens, are composed of millions of pixels which are made out of 3 smaller subpixels, each in control of one color, red, green, or blue. By changing the value of each subpixel, any color can be displayed. An LCD screen is made out of the backlight, horizontal and vertical polarizers, transparent electrodes, liquid crystals, and a screen, all working together so you can watch your favorite shows. The backlight emits both horizontal and vertical polarizing light, which passes through a filter, filtering only horizontal polarizing light. Now, as the name suggests, they use liquid crystals in order to change the value of every single subpixel. Depending on the color required, transparent electrodes will align liquid crystals to alter the filtered light, allowing it to pass through the second filter. The double filtered light finally hits the screen, producing a value for the subpixel. This value increases depending on how much light it receives, scaling from 0 to 255. This means that every pixel is controlled individually, making for precise displays.
LCD screens are truly incredible and fascinating. Thank you for watching.
now that's how LCD screens work in general. The exact way that modern LCD screens work is a little different. Turns out it's a little more efficient to twist the light and then twist it more or twist it less. But it's basically the same idea. Instead of going from 0 rotation to 90 degrees, they go from like 90 to 180. It turns out it's just more efficient that way from an electronics and switching standpoint and stuff. But yeah, so that's how LCD screens work. Now, more expensive, if you have like an OLED screen, that will work differently. OLED are little actual LED lights for each subpixel. And the O stands for organic, which is how they can get it small and thin like that. So that's all for today. I'll see you all in not next week, but the week after. Have a nice Thanksgiving. And we will continue on and finish off the chapter then.